Hey gang, and welcome back for another, you guessed it, worksheet, solutions, walkthrough for the worksheet. More challenging alpha carbon reaction and synthesis practice. Okay gang, so I know if you're sick of this stuff, it's probably because you've been doing a lot of practice, which is a good thing. I hope this stuff is starting to make some sense, but I'm assuming you've seen this worksheet. It was designed to be hard, so if some of these didn't make sense, that's okay. That's why you're here. You know the drill. Worksheet solutions walkthrough. We're going to go through the worksheet. I'm going to show you how I arrived at the answers that you've already seen in the solutions PDF. But enough my yabbering. Let's get after it. Okay, gang, so for problem 1, there are 9. Either complete the reactions, fill in the reagents, provide the reactants, type of reactions. So what I want to do is take them 3 at a time. So this is going to be part 1 of 3 because, like I said, I wanted to make these hard. And they are like pretty bearish complete the reaction problems in my opinion. Okay, so if we take a look at this first one. So, there's multiple steps. So we, as we always do, take it one step at a time. So if we look here, we see a ketone. And in this first step, I think what you're seeing is formulating kinetic enolate conditions, right? We have big bulky base, super cold conditions, right? It's a little chilly. So we're going to be making the enolate that's on the less substituted side in terms of the alpha carbon, right? We're going to be making our enolate this direction versus this direction, right? So if I wanted to, what I could do is I could draw my enolate like this if I wanted to. And then I hope you can see ethyl bromide. So all of this first and second step, all this is going to be getting us to do is doing SN2 with an enolate, because I feel like that's overlooked so easily. You're enamored by, and I was too, the Aldol reaction, the Michael additions, the Robinson Annulations, but you can do plain old SN2. Okay, so remember these would swing down. Remember the alpha carbon is the carbon doing the bonding. The alpha carbon would attack the ethyl group from the backside. So after the first and second step, I'm now going to move over here. We have that methyl group has not moved. We've reformed our carbonyl, remember? And all we've done is alkylate that position right there. So there's an ethyl group where there wasn't one before. But we're not done. We're not out of the woods. And I threw this in just to make sure you don't forget. All that ketone and aldehyde chemistry, still valid, still fair game. So what I hope you're seeing here is this is a primary amine where you have acidic conditions. No more is someone going to write minus H2O explicitly, but hopefully this was enough for you to think imine formation. So remember, we're going to form an imine right here. And remember what an imine is. All right, here comes our product in black. So we have the ethyl group up here. We have the methyl group down here. And remember, it's going to be an N double bond to a carbon, nitrogen, carbon double bond. And then this, whatever your R group is along for the ride, right? And if you want to, you can explicitly draw the lone pair right there, but you're going to have a nitrogen double bonded to that carbon. The alpha carbon up top is going to be alkylated with that ethyl group. You're going to have the methyl up here, and that methyl is just chilling along for the ride. So this is our answer for the first part of problem 1, okay? So now, moving down to here. Again, we're seeing those kinetic enolate forming conditions. So we have a dicarbonyl here, but, no one specified more than one equivalent, so just assume one equivalent, okay? So I'm going to cheat a little bit. What I'm going to do is I'm going to form the enolate over here. It doesn't matter if you formed it over here, you've got the same product. I'm going to cheat. So after step 1, we have this right here. Now here's where things get wacky, gang. I hope you're seeing this heat, okay? What we're about to do is an aldol condensation in base. What I really, maybe I should have also put NaOH and water. Maybe I'll fix that on the worksheet. But this is going to be a homoaldol condensation, right? And not even just a homoaldol, right? Homo because, well, actually that's a lie. It's not even really. It's an intramolecular aldol condensation, right? So strike that, not a homo aldol, just an intramolecular aldol condensation in base. So what was actually going to happen, remember, as these electrons swing down, we reform our carbonyl. It's this alpha carbon now that's going to loop around, taking these 2 electrons, right, in that double bond, attacking right here, and these electrons kick up. So if you're thinking to yourself, my goodness, are we forming a 6-membered ring? You better believe it. 1, 2, 3, 4, 5, and 6, right? So we'll number these because numbering helps. Very few situations where it does not. So this is kind of steps 1, and then the blue arrows are showing step 2. So again, I'm going to kind of draw the blue all the way over here, and I highly recommend drawing a 6-membered ring like this because we know we formed one. I'm going to use the red marker to then mark our 6 carbons, so then I'll just do like a red to red mapping. So what you can see is nothing interesting on carbon 1. On carbon 2, we have the carbonyl that we reformed. And again, you didn't have to have this exactly the way I did, but I think it helps. Numbering, at least. Could have numbered the other way is what I mean. Okay, nothing on 3, nothing on 4, nothing on 5, and on 6, we're going to have a methyl group outside the ring as well as an O-, okay? So on 6, we have a methyl group, and then up here we have an O-. So, reason why I should have kept the OH and H2O, we know this will get, the negative charge will get quenched by some source of proton, probably water, and then remember, the heat and base, they add to actually, in basic conditions, right? That's not an amazing leaving group in hydroxide, but if we add in extra energy, we can get it to go. So remember, we're going to do alpha deprotonation yet again. So some base will come along, another hydroxide, and remember, this is aided by the heat, right? We're going to deprotonate. These swing down. We drive off our bad leaving group. And remember, so this aldol intramolecular aldol condensation gives us, there's a reason why I'm drawing this in blue, gang. Maybe you're picking up on it. So this is after step 2, okay? So I'm going to erase this over here now. Actually, I'll do this work down here. So we have a third step, HBr. Now, this is probably going to be maybe the reason why you're like, what is going on with this, Joe? Don't be surprised. I've seen this problem asked before. So, and the mechanistic arrows might go a little bit differently. What's essentially going to happen is that this will grab H+, will then give you bromine, the Br- floating around. The point being is that you're going to have this carbonyl oxygen protonated. That only makes the positive charge on this carbon stronger because the resonance will want to align itself such that this negative charge on oxygen is not there. So once this is protonated and this is that hydrogen from HBr, Br- comes in, soft nucleophile, it is going to do a 1,4 addition. Okay, so at first you have this enol, you have this and a bromine, but then the enol tautomers to the ketone. So, I know I'm going crazy everywhere. Your final product is actually a carbonyl here, the original methyl group, that's this methyl group right here, and then a bromine, okay? So I'm gonna let you take that in. You can stop the video if you want to, because I'm gonna erase it and make room because we have quite a bit of a problem coming right here. Okay? So again, that ending part, this picks up H+, you attack, make an enol at the end, it flips back to its ketone form, very similar to how you do a regular 1,4 addition, right? With like a cuprate or something like that, or even a Michael addition for that matter with an enolate. So let me bring this back. Okay, gang, so I paused to erase because we're gonna need some space. So if we take a look right here, nothing out of the ordinary for the first step of this reaction. I think what you can see is we're going to do alpha deprotonation, right? We're going to make an enolate. But we actually only have one way to make it, and that's why we don't see thermodynamic or kinetic conditions, because there are no protons on this alpha carbon right here. We can only deprotonate over here. So after step 1, we have the following enolate. Okay, now what you can see here, we see an alpha beta unsaturated ketone or an enone, and then we see NaOH, H2O, and heat. Unbelievably, what this so shortly is suggesting is that we have an enolate, we're going to do a Michael addition, but it's not going to stop there. These are conditions for a Robinson annulation. Okay, so what I would highly recommend is just doing the Michael. I think that's not terrible to do just predict it, and then take that Michael and then get the rest of your product. That's how I do these. I know it's long, but like you want to get it right. So let's draw this. So what's going to happen is that this is the Michael addition part, right? Because a Robinson annulation is nothing but a Michael addition followed up by an Aldol condensation in base. So we swing these down. It's this alpha carbon. It's calling the shots. It's going to do a Michael addition in this way, right? So if we're going to draw this product, what I like to do is redraw this. I'm going to flip this methyl group down, okay? Because this carbon right here, this dot carbon, is going to be bonding to this carbon I'm asterisking right there, okay? So leave the T-butyl group. It's now this carbon with the down methyl group that I dotted. The next line is to that asterisk carbon, which is one of, so it is 1, 2, 3, 4. So 1, 2, 3, 4. And remember, so 1, 2, 3, there's a carbonyl, 1, 2, 3. And you can double check yourself by 1, 2, 3, 4, and 5. There's the Michael addition. We did it correctly. Got the 1,5 dicarbonyl. Now remember, it's at this point that we need to make a 6-membered ring, which is why we go back to our original carbonyl, or sorry, the carbonyl we just did the Michael addition on that piece, and we're going to make an enolate this way because you can see 1, 2, 3, 4, 5, and if we make an enolate over there, we can then attack and loop it around and get 6 carbons. So what I hope is not too hard to see is I'm going to redraw this like this. So 1, 2, 3, 4, 5, and 6. I'm going to have these swing down. I'm then going to loop this around. That's a really inefficient arrow, but we've just formed a 6-membered ring. So what I'm going to do is just draw a 6-membered ring. I'm going to draw a hexagon. I know that's super crazy to be like, how you're just going to draw it and then visualize it? No, visualizing that would make me go crazy. I'm just going to trust my numbers. So on 1, right, I'll just do this 1, 2, 3, 4, 5, and 6. So on 1, I have nothing. 2, I have a carbonyl. Whoops, wrong color. 2 carbonyl. 3, nothing. 4, 5. Okay, with the methyl. 6, we're going to have an O-. And then also on 6, we're going to have a T-butyl group. So really nothing crazy going on. And then remember, this will get worked up by the water. So really after this step, you can just, I'll put like water in here. And then remember, it's aldol condensation time. So the condensation, right, we're going to go to the alpha carbon. We know this is all about getting that 4-atom conjugated system. So right, we bring in some hydroxide, we deprotonate, these swing down. The heat provided helps us overcome the fact that this is a terrible leaving group. And then we make our final product, right? So you're going to have 1, 2, 3, 4. There's your alpha beta unsaturated carbonyl, your enone in this case. And then I don't want to forget this right here. Let me just double check. That is exactly how this Robinson annulation goes, which I know it's crazy. You're like, that's so much for a complete reaction question. It is. You usually don't, in my experience, see these in a complete the reaction section, but I wanted to show you it here. And it doesn't really take that much time. I don't know, do the Michael, do Robinson, or do the aldol condensation. It didn't take that much time. Okay, that was the first 3 of 9. So let's go from part 1 into part 2. Okay, gang, rolling into the second part of problem 1. 3 more, 2 complete the reactions, 1 provide the reagent type problem. So if we take a look up here, kind of an interesting thing going on. We have a bromine off of our alpha carbon and we have a ketone. So in this first step, we see a familiar friend, T-butoxide, right? And when we see T-butoxide, we think big, bulky base, likes to do, it does E2, and usually, because of its bulk, Hoffman product. We eliminate and create a lesser substituted double bond. It's easier to grab that hydrogen because of the fact that T-butoxide is highly branched and bulky. So, given what we know now, you see where I'm leading you in this first step of the reaction. We're going to do E2, and we don't even have the option to eliminate over here. We need a neighboring hydrogen to rip off. Well. Looks like this is a great place to rip off a hydrogen, have bromine leave as a leaving group. Just to draw some arrows. And look at that. What this forms right off the bat is an alpha beta unsaturated ketone or an enone, right? So just a little disguising of the first step to give us an enone. And now what I think you can see, I'm going to move this over here to give myself some working room, is that we're going to be doing a Michael addition. Okay, we have, I'm including the OLI right here, and we're going to have this enone that we generated over there. Okay, so what's going to happen is we reform the ketone. It's this alpha carbon that's calling the shots. Never forget that. It's that alpha carbon that's going to swing down, attack the fourth carbon, because we're doing a 1,4 addition, but it's more specifically a Michael addition. These electrons bounce over here. We get this up here. So if I want to draw this, because we're not done, we have a third step. If I want to draw this after the fact, I'll have a carbonyl in the benzylic position right off the benzene ring. And remember, right, if I want to count 1, 2, 3, well, it's because I already drew this one. Right, if I want to do 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And I have one more methyl group right here. I know this will not, it'll look like this at first, right? This with an O minus, but I know that will flip to the ketone, right? So I'm going to erase this really quickly. This will flip back. Okay, and you can see we did the Michael addition correctly because 1, 2, 3, 4, 5. All right, but now, again, more of that, aldehyde carbon or ketone chemistry coming back. This is a peroxy acid, the Baeyer-Villiger oxidation, right? We know we have to think about migratory aptitude here. And in fact, what we need to do here is actually, we don't even have aryl as an option. So right here, we're going to insert an oxygen right here, right? Because that's secondary. And between this primary and this secondary spot, secondary wins out. So remember, the Baeyer-Villiger oxidation creates esters. So what we are actually going to be doing here is lengthening our chain right here, putting an oxygen next door to, kind of pushing our alpha carbon and then inserting an oxygen. And we're going to do the same thing over here because we have excess. So all that's going to happen here, gang, so just one, we have 3 carbons between the carbonyls, right? We can't forget that. So it's on either side of these that will have an oxygen. So hopefully you follow me on this. Here, I'm going to do this really quickly. I'll draw this down here. 1, 2, 3. This is our product after the Baeyer-Villiger oxidation. So you can see we still have 1, 2, 3, 1, 2, 3. It's just these new oxygens inserted here and here because of that's how the migratory aptitude worked out. Okay? And because we had excess. If you didn't, it'd be tough to, it wouldn't be a judgment call you could make in terms of which one would get the oxygen and the oxidation. Okay, over here, so what do we got? Hopefully what you're seeing here is this is screaming out to you enamine, right? Because we see a secondary amine, we see an acidic environment, right? No one's writing minus H2O anymore. So there's only one way to make this enamine. So after the first step, what we look like looks like this. And if we want to be technically correct, it won't really matter at the end, right? This is the alpha carbon right here is this alpha carbon. And we have 2 others. We technically should draw it like this. It's not going to make a big deal though. It's not going to be an issue. People often forget that enamines are nucleophilic. You can do the same things with enamines that you can with enolates. They're just a little less nucleophilic. All right, so I wanted to toss this in because it doesn't look, this probably was very, weird if you've never seen this before. I'd never seen this, I didn't even see this when I took the class, but I saw it when I was working with a student. I thought it was so good I had to toss it. So what is weird is this is a non-traditional 1,4 system. 1, 2, 3, and 4, okay? We can still draw that same resonance where we do this, and this carbon gets a plus charge. So for all intents and purposes, think of this like an enone, okay? I can even put a hydrogen here. Think of this as an enone. So what's going to happen is this enamine will see the carbon on the end, okay? This carbon, the fourth carbon, the nitrogen swings its electrons down. This alpha carbon takes control, attacks here. These electrons bounce, these electrons bounce, okay? So I'm going to move over here now, and it's going to be a little bit of a hot mess. But I'm also going to 1, 2, 3, 4. So we have 4 carbons. 1, 2. Actually, I'm going to draw this very similar to how we started. So you can see 1, 2, 3, 4. But it's this carbon right here that just made the new bond. Okay? Who's it to? It's to this carbon that I'm going to dot right here. Okay? So once we've done that, I need another carbon, and then the nitrogen, and then I can draw the O minus, and then the O minus, and there's a double bond right here, and a plus, okay? Now, what does the H3O plus do? It does 2 things. It's going to help wipe away this enamine and recover our carbonyl, and we're going to do some work down here as well, which, again, if this is brand new to you, don't worry. I just thought it'd be fun and good to kind of expose you to it if you haven't seen it. So what's going to happen is we know how reverse enamine, unraveling an enamine works. So the H3O plus is responsible for that, right? We know with H plus of water, that's how that works. Pump water back in, the equilibrium shifts back to the carbonyl. Now down here, what will happen is we're going to end up back with a nitro group. Similar to how you get the carbonyl back when you do a 1,4 addition or a Michael addition. So we will reform this nitrogen-oxygen double bond because we want to get the nitro group, the NO2 group, back. And then this double bond right here, this carbon uses to grab H+. So what do you get at the very end? So once this happens, you can redraw that as NO2, okay? So I know, sorry gang, I know I'm like all over the place. But once this happens, you have the following 1, 2, 3, and then just NO2, which inside there has a minus on the oxygen and a plus on the nitrogen, okay? And 1, 2, 3, okay. Oh, I added a carbon. Okay. Finally, this bottom one. So because it's filling the reagent, I almost like to do these backwards like mini syntheses. Let's see if you like the way I'll explain this. So one thing that I think is important to do from here to here, and similar to how we approach synthesis questions, at least I like to count my carbons. I like to kind of, if I'm given strict starting material, identify what I've been given in my target molecule, and I hope what you can see, and it's not always a given, but I think what you can see is 4 carbons right here, as well as the presence of this oxygen right here. So I think I see these 4 carbons because there's just 1, 2, 3 down there with a double bond. And I think you can see that a reduction must have been done on this oxygen right here to get this OH, and there's a plus enantiomer. As we can figure the deuterium out later. So what I think as a first step backwards, I must have had some type of reduction done. And the other key thing is it didn't affect that double bond, right? We know double bonds are sensitive to acidic environments because when we reduce carbonyls, we have 2 options. We either have lithium aluminum hydride, and I'm ignoring the deuterium for a second with acidic workup, or we have, our sodium borohydride with an ethanol workup, which if you compare the 2, I hope what you can see is some people will give you grief in this type of scenario if you use lithium aluminum hydride and the acidic workup, because this will do a Markovnikov addition of water on your double bond. So in this scenario, the best thing you can do is use sodium borohydride and ethanol. And not even just that, we need the attacking, right? The thing that will attack the carbonyl-carbon needs to be D- deuterium. So that means we need NABD4, which is a source of D-, and ethanol is a workup. Or like methanol, ethanol's typically the popular pairing, okay? So now I think you can see something a lot easier to work with. What I think hopefully you can see right here is something attached to the alpha carbon. Now we're cooking with gas. And not even just that, we have an asymmetric carbonyl. So I think we had some type of enolate like this that attacked 1, 2, 3, something like this. And that's a good leaving group. I'm gonna probably pick a halogen, right? Because if we did this, and then that would give us this product. We'd recover our carbonyl. So I'm actually gonna just, on the solutions, I used I as an iodide. You could use chlorine, bromine, whatever. So the next thing is, so almost as a third step, we had NABD4 and ethanol, put a comma there. For the second step, we had this allylic iodide right there, okay? And last but not least, we need to obtain this enolate. So I hope what you're thinking is, this versus this is a thermodynamic enolate. So I'm going to be reaching for the small base, the warmer conditions, and THF if you want style points, okay? So this gives us this nucleophile, which we can alkylate on the alpha carbon to get this right here, and then all we need to do is reduce that with NABD4 and ethanol. Whew, okay gang, I know these are long, but you paid the money, and I hope this is your money's worth, okay? So, part 3, and then we will close the book on part 1 and speed through 2 and 3. Okay gang, final 3, part 3 of problem 1. So if we take a look right here, okay, right up there, we have to provide the reactants for this reaction right here. So I hope you're seeing a few things. One, you're seeing these dreadful, simple, but devious reagents, right? And you see a whole bunch of stuff right there. And, you know, I hope what you're seeing is this, and a 6-membered ring. So this right here is actually a Robinson Annulation product. And unlike most of those problems I peppered you with in that previous worksheet, the more simple, like we're doing Michaels, we're doing Robinsons, we're doing Aldols, you know, this only has 1 carbonyl left over. So what we can kind of infer from that is that with the only 1 carbonyl left, there was an, you know, alpha beta unsaturated carbonyl, an enone of some sort probably, that we attacked in the Michael addition and then the subsequent, you know, used it in the aldol condensation, but we must have just done it with not a dicarbonyl, but just a regular carbonyl as the initial enolate. So that whole, you know, breaking up the bonds, that still applies, okay? This double bond is still a point of breakage right here, okay? Because we know, you see how 1, 2, 3, this must have been where an OH was after an aldol reaction, which then proceeded to the condensation, right? Because of the 1,3-hydroxycarbonyl. So, at that point, right? So we know this is a key spot right here. This used to, if I even want to walk, you know, pretend the double bond's not there because I'm about to break the octet rule. This used to be an alcohol, which means that used to be a carbonyl on the initial product. So that will help us out. Now remember, we had to get this party started by doing a Michael addition, which means this carbon right here, if I did 1, 2, 3, 4, it must have been an enone, and that 4th carbon had to have been on the initial enone part to get attacked. By whom? The alpha carbon on this initial piece over here. So where do I draw this line? Right here. Just like you would if you're working with a dicarbonyl, but we're not working with a dicarbonyl. So if we take this, hopefully as I put this together, it'll start to make sense. So my initial piece right here that was the enolate looks like this, right? So you can see that's this right here. And then I have, 1, 2, 3, 4 I'll draw. So right up top I have the ethyl. Right up here I have the carbonyl. This methyl is still there, double bond right there. So hopefully what you're seeing is that we would initially have this attack up here, do this and whatnot, and that's how this will go. But, it's a little bit easier to show that whole like striking through the double bond and kind of curving it to cut your two pieces with the dicarbonyl, because you have a little bit more evidence of this thing. So that's why I threw so many dicarbonyls at you. Okay, that was it for the first one. Let me just make sure I didn't. Yeah, that is, you can have this, or if in the answers, I think I may have put this, I'll include both actually. You can include either. Both would be fine, both would be correct. Okay, now down here, no basic conditions. What we're seeing here is your classic 1,3 hydroxycarbonyls. So you're probably thinking, okay, why'd you go soft on us, Joe? Well, I had to throw in a little curveball, a little wrench at you. So no basic conditions, which means you can't just make an enolate and call it a day, right? So we know we're going to be attacking with the alpha carbon. We know we're going to be making a cut here, and we know this is represented in our product right here. However, we need some type of different nucleophile. And remember how earlier just in this video I talked about how enamines can be just as nucleophilic, just not as much, but close to that of an enolate. So you need to make an enamine, which remember means we need a secondary amine, right? Because if we can't use basic conditions, why not use acidic? Let me just make sure I'm using the same, right? You could use diethylamine, or you can use that amine that has the, it's the 5-membered ring like this. Just use some type of secondary amine, okay? And then make sure to include acidic conditions. You can write H+, you can use a specific acid like H2SO4. Just make sure to finish off. So this will form our enamine, and in this situation, that would look like this. Nitrogen with this and this. This makes your carbon nucleophilic. Then we need to actually toss in the thing we're going to be attacking, which you can write it again. It's just itself, right? So it does help to just toss it in again, because you can assume that all of this was converted to enamine, and then you can follow that up with H+ and water, because we're going to have to unravel that enamine, because right after we do the product, you do the attack at first, we will have this, and it's only step 3, the H+ and H2O, that unravels this enamine and recovers the carbonyl. So this is the answer. Yeah, let me box some of this stuff, because this has been a crazy video so far. Okay, cool. Now, last but not least, down here, you might be thinking, whew, straightforward, and for the most part it is. So we have this lovely reactant right here, but hopefully, I think you're probably honing in on the copper right here. You're thinking cuprate, you're thinking 1,4 addition, you're thinking it's going to attack here, and I'd agree with you on all of that, right? We have the pH, which remember, pH is just a phenyl group, right? You're attacking with an aryl carbon. Aryl meaning on this carbon it's part of the benzene ring. So how does this go? Just as you expect it. When we attack here, this bounces here, we kick this up. And what I'm going to do is I'm going to draw this in blue. I'm going to draw it up here. So we have this at first. That's so 1, 2, 3. So 1, 2, 3. And then the phenyl group, the pH. We know that enolate-ish thing will flip back to its carbonyl form. So right after the 1,4 addition, right, we still have, if you were number 1, 2, 3, and 4, it's clear that the phenyl group is just attached at the 4th carbon. Well, what do we do here? Remember this is an EAS reaction. This is a nitration. This is going to put a nitro group on a benzene ring. But I was sneaky about this. And what you need to do is actually expand that pH, because what we have here now is 2 benzene rings. We have the option now to nitrate one or the other. And remember how we do that. We look at each ring. If we look at this right here, I hope what you're seeing is, this is an electron withdrawing group. It's a partial positive atom directly off the benzene ring that's sucking electron density out of it, deactivating it. Over here is not the best electron donating group in the world, but we have an alkyl group. So this ring is more reactive in terms of subsequent EAS reactions than this one. So we're going to only focus on this, and at that point, this becomes a giant group. We know alkyl groups are ortho-pair directors, so the product looks like this. Nothing is different. I'm going to erase this. Nothing is different about what we just had, but we will have the nitro group para to that big, big, big group over there. Gang, these were supposed to be hard. I'm not saying that you can do anything if you can do these, but if you can reason your way through these, I can't imagine that much can get thrown at you that you can't reason through yourself. Okay, that was the first of 3 problems. We have a quick concept problem, then we have 2, I promise, much quicker synthesis problems than everything we just did. So stick with me, hang tight, and let's keep going. Okay, gang, in problem 2, we are shown 2 reactions, one of which we observe to not occur. The other we observe does occur. And if we look at what's actually happening here, at least in the one that works, we see we have alcohol in both scenarios. Obviously, its placement probably is what makes the difference. Spoiler alert, it does. And we both have acidic environments. We have H2O, and you can see we form our alpha, beta, unsaturated carbonyl or enone, whatever you want to call it, okay? Now, here's what's important to remember. Water is not basic. So how is this working? Let's at least look at the one that works. Let's try to figure out why this works, and then we can figure out what is wrong about the top. Well, it's no surprise that the first thing that's going to happen is that this oxygen in the alcohol will grab H+. We will then form a good leaving group, and then through solvolysis, it will leave, okay? So we then form this carbocation, which then this water, we have tons of it, will come by. It will then do an E, so this is kind of an E1 type, flow. It is an E1 flow. We then take off that proton, and then we form the enone, okay? So really, it comes down to the fact that this alcohol is in a really good position for solvolysis to occur, and then the water grabs proton, E1 occurs. It sets up the formation. Goodness, I can't hold on to my markers. So excited about the conjugated system, okay? That's why this works. Now let's see as to why this does not work. Well, let's just see what this initial carbocation would look like. And now I think you can see the problem. And if you don't, the problem is that this is a strongly partially positive carbonyl carbon. We now are trying to form a straight up positive charge next door. There is going to be an electrostatic repulsion going on here. So that's why this does not work. It's because of this partial positive charge and this positive charge butting heads, repelling each other, making this move from here to here more unstable, higher energy than it would be if there's this extra distance of carbon distance in between the carbonyl carbon and what becomes a carbocation. So I can't hold on to my markers. I can't talk. It comes down to the oxygen being in a place that's 1 carbon away. The carbocation does not have that much repulsion relative to the partial positive carbonyl carbon. The E1 has no issue finishing, but up here it's just a little too close for comfort where the carbocation forms and the partial positive carbonyl carbon. Gang, that is it for problem 2. 2 synthesis problems. Problem 3, they're not that long. Let's finish this walkthrough. Okay, gang, in the first synthesis problem, this is A. We have the following starting material that we have to use, and then the target molecule, I can't talk at all, that we're trying to get to. Okay, now you know me. I like to count carbons. 1, 2, 3, 4. And I think it's no secret that we see 1, 2, 3, 4, and we definitely see this is our starting material. I've never abbreviated that SM, but today's a new day. Okay? So, I think here's what we did. We see this, and we pretty clearly see it in the target molecule, but we see a group right here off of, that's right, you guessed it, our alpha carbon. So we must have alkylated, but we want to make sure we do this in a very efficient way, because this is, I'll explain. So what we want to do first, though, is we certainly don't we don't have a carboxylic acid throughout the problem. I think that happened at the very end. So break out your sodium dichromate, H2SO4, your Jones oxidation reagents. That will then give us this aldehyde at the end. Okay, so now it's time to cut this in half, okay? I think, so what will be easy, I think, to pick out is that we had some type of isopropyl halide, like an isopropyl bromide would be super good and easy, and then this is actually, it says we can use any organic material, so this is like starting material as far as we are concerned. Now here's the thing. We could have this, but enolates are basic, and that's a secondary substrate. We would, if we did this, end up just doing some E2, and that's no good. We would end up with just this. So this problem, the kind of, the kink in it, is that you don't want to use something so basic. We actually want to use an enamine, okay? I'm bringing this up so many times because it is such a popular thing to include on tests. I just made up my nitrogen source. You'll see me kind of show where it comes from after the fact. And because we're showing this SN2 happening, right? I don't have to draw the arrows, but I'm doing that just for clarity, right? You'd want to put H2O and H plus over this arrow so that someone would know, okay, they know that once this attack happens, this is going to unravel the enamine and give back the original carbonyl it came from, okay? So now where do we get this? I'm going to erase these arrows. Where do we get this from? Oh my goodness, that was such a waste of time. Okay, where do we get this from? Well, we know we get enamines from carbonyls, so we must have had this. We need acid, right? And we need some source of secondary amine. You can use whatever secondary amine you like. Doesn't have to be the one I used, but just make sure whatever's here and here matches up. And I think you know how to do this. Oxidize an alcohol to an aldehyde. Good old PCC. Okay, gang, that was A. Let's finish this walkthrough with B. Okay, gang, to finish this worksheet out in the interest of time, I'm showing you the synthesis 1 because this video is getting long, and 2, this is a hard one. If you did this on the first try, jOeCHEM is officially yours. I hand it over. But if you can look at this, understand it, and even reproduce it, then I really think you're in good shape. Okay, so if we take a look here, right? Starting at the end, because looking here is scary, seeing that we have a 5-membered ring with a double bond. Somehow we get a 6-membered ring with a double bond. So I promise it will make sense by the end. So what I want this takeaway for you, from the end, a takeaway that would be a good starting point, would be seeing that we must, oops, I can't count. I hope you're seeing evidence of an alpha-beta unsaturated carbonyl, an enone, okay? At some point, this thing must have looked like this. It doesn't right now. We have actually an ether with that oxygen, so we must have done some things to it. But if we can get back to this, that would be a good starting point, okay? And in fact, because what I forgot to do, and I always say it all the time, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. All these carbons are in there. This is just extra decoration up top, okay? So if we had this, I think you can see we could have reduced this down to an alcohol, and then we could have deprotonated that alcohol to then be nucleophilic, and we could have attacked some type of, alkyl, methyl halide of some sort. So stepping this back, I'm gonna, that's the CH3 up here. You're going to say, okay, stepping this back with the CH3Br. Now I have this alkoxide. And how did I get that alkoxide? Well, I got it from an alcohol that I deprotonated with a strong base. Yeah, I used butyllithium here. You could have used LDA. You could have used T-butoxide. You could use NH2 minus, whatever you like, as long as it's a strong base, okay? Now remember, I'm hitting you again with that. We know we have this OH here, and we need to get back to this carbonyl to get the enone, to get the alpha-beta unsaturated carbonyl. And yes, I'm hitting you again with, be careful with how you reduce. I'm gonna use sodium borohydride and ethanol here because if I use lithium aluminum hydride with the acidic workup, I might tamper with my double bond on accident, and we don't want to do that. We have our double bond untouched the whole way through, okay? At least up to here. Now, here's maybe the biggest, hardest part of this synthesis. You're seeing this enone right here. I'm just gonna make sure I don't lose that. Where did it come from? And how did we go from this to that? Clearly we expanded the ring. How did we do that? Well, hopefully you remember, and this is the hardest part in my opinion, that you get these alpha beta unsaturated carbonyls, you get these enones from doing aldol condensations, okay? It's key to know that relationship, and it is, with all the craziness, it's hard to bring that back to the forefront of your mind. But if we were to step this back or even step this forward, we clearly need to open this 5-membered ring up. We need to somehow get into a position that can then rewrap itself back into a 6-membered ring this time. So if we were to cleave this bond right here, right? 1, 2, 3, 4, 5, and 6, 7. We would then get a dicarbonyl, right? We get a carbonyl on 2 and a carbonyl on 6 using ozonolysis, right? Doesn't matter what your workup is here because we actually have internal carbonyls, so you're gonna get ketones no matter what. And it's at this point, right? We know if we make an enolate this way, that would then, and then we get some type of, intramolecular aldol reaction that then goes to a condensation. That would be 1, 2, 3, 4, 5, lucky number 6. So we actually did this. This is, I believe, one of the first complete the reaction problems. We already worked this out, and with the condensation, we got this. We then just used HBr to do another 1,4 addition with it. But that's how this works. I know it's crazy, and like I said, it's a hard one. So if you can understand it, mad props. Really. And if you got it right, that's like, I don't know, that's amazing. Great job. So, if you can rework this, that's good. And, if you got on the first try, tip my cap. Whew. Okay, gang, this monstrosity of a worksheet is finally over. Thank you for sticking with me. You're amazing. And the fact that you're watching this video means not only that you're amazing for watching jOeCHEM and using it, but also financially supporting the website. You don't have to watch the videos. You don't have to pay me a single cent, but I appreciate that you did. And I appreciate that you're using jOeCHEM to help you conquer carbon. I hope it's exactly what you were looking for. I hope it's helping you, do as well as you want to. And no matter what, I hope to see you all in the next video.